Hello, everyone. I'm going to go ahead and derive a moment of inertia for a cylinder, and I'm going to be doing it with multiple integrals this time. I'm actually going to use the common variables that we use for cylindrical coordinates. In fact, even though I don't necessarily have to even call it cylindrical variables or a cylindrical coordinate system, but we will be using multiple integrals. So I thought that might be somewhat helpful for those of my students that are actually trying to learn multiple integrals and actually are curious how they would apply it because it's so much easier than having to make up an integrand and all that good stuff. So let me begin by sharing my iPad screen. So the problem is a cylinder has a thickness T, a radius R, and its mass M is uniformly distributed throughout the cylinder. Use integration to calculate its moment of inertia when rotated about an axis perpendicular to the disk through its center. So that's the actual problem we're going to solve. I'll start off as always with the solution statement. What we are given here is that it's a uniform cylinder. And what I mean by a uniform cylinder is a mass of the mass of the cylinder is uniformly distributed. So this will be, I'll call this in short a uniform cylinder. And what that means is the rho r lambda r sigma is equal to a constant. That's what we mean when we say the mass is uniformly distributed, because every particular unit of volume or length or area has exactly the same mass as every unit of volume or length or area. We also know I is equal to the integral of r squared dm. We also know dm can equal lambda dl or sigma dA r rho dV. And we also know that the cylinder has a radius r, a mass m, and a thickness t. So I'm going to start off by drawing this in coordinates, and then I'm going to do some drawings to represent the actual differential volume element that I'll be using. So let's start off by drawing a coordinate system using some of the tools of my note-taking app. So that's that. Now I've actually allowed the app to actually make sure those lines are straight and perpendicular and all that good stuff. Now I'm going to try to use those lines, or excuse me, the app again to try to make a cylinder that is drawn in 3 dimensions and looks like a cylinder, hopefully. But before that, let me go ahead and try to draw a z-axis as well. This is a right-handed coordinate system, as all coordinate systems should be. And actually, I didn't have the auto draw on in that case. So in this case, X, Y, and then using the right-hand rule, we should come up with Z pointing out of the page right here, like this. And that's what we got. I'm going to go ahead and draw the cylinder in the page. What I'm going to do is I'm going to mark off some spots where the cylinder should hit so that I can draw out a better cylinder than normal. So I'm going to bring it all the way out to 4 here, and then I'm going to bring it all the way into here, and then all the way out to 4 on the other side, which be right here. So I'm going to try to hit these points, and hopefully by hitting those points, the application will make the oval ellipse shape better or close to perfect. Something like that. Uh, didn't do so well. I'm going to try one more time. Like that. That looks pretty good. Now I'm going to try to mimic that same thing. Hopefully I can do a copy paste. It's not letting me do a copy paste, so I guess I'll just have to draw another. And that one's going to have to go through this mark over here. It's also going to have to go through this mark over here. It's also going to have to go through this mark over here. And then finally right there. So let me again try to use the app to draw this appropriately. That doesn't look too bad. It's not perfect, but it's good enough, I guess. And then I connect this, of course, because it's a cylinder. It's attached that way, and I can make the back parts look like they're back parts by making this line a little more dashed than it is. Maybe one more right there. So there's our actual cylinder. And what I'm mentioning here is this cylinder, oops, erased everything. This cylinder has a radius R and a height T, and it has a mass M, and its volume, which is dm over dv, is just going to be m over pi r squared t. Now this time I'm free to use a double integral, so I don't have to look so hard for exactly the right shape and then make up, little formulas like 2 pi r dr times t and stuff like that. I'm going to do a slightly different one. I'm actually going to imagine a differential volume element within this that is three-dimensional. So what I'll do is I'm going to first imagine a line going out at some angle theta that's into the z direction, but in other words, in the negative z direction, but it started off at a theta equals 0 at the x-axis. So we're sort of going to draw it that way. Actually, with this in mind, let me go ahead and flip these axes just to make it a little neater. Instead of putting the z as the one coming out of the board, which it almost looks automatically like it's x coming out of the board, what I'm going to do instead is make this one up here the z-axis, because then it's more consistent with uh, the drawing I was getting ready to do. So if we call that Z and we call this X and then we call this Y, it's still a right-handed coordinate system, but that R that I just drew is a better match. I just have to now change the way I'm going to draw this because it's was set up with the axis being a little funny. So let me just try to finish this out as it was. So that fixed that. I'm not too worried about the little bit of black in there. But now what I'm going to do is I'll realize that this line right here is parallel to the x-axis. So if I wanted to go out an angle theta, I would pull out this angle theta right there, and then I would allow a line that goes all the way to the edge, and then I'd allow the angle to vary by a little bit called d theta, and this one's going to now go all the way out to this edge. And what I will say is my differential area element could be a shape like this. Actually, that drawing didn't come out too good, but it's going to start off like that. That'll be the width. And that width, of course, is depending on how far you go out in the axis, it would be r times d theta. That would be the measurement of that little arc along here. If I looked at it from above, it'd make a little bit more sense. So what I'm now going to do is go ahead and draw a circle to get you a better feeling for what this would look like from directly above. So let me see if I can draw a circle. I'm going to give myself some marks again so I can get this to draw a fairly precise circle, fairly like I want it. So I'm going to do this. Oops, and I don't have it on the right. Oh, I did actually have it on the right button. Okay, so I'll start it here then. So there's my circle. That's supposed to represent the cylinder that we're looking at right now. And I also want to mention that it probably would have been better to draw that in blue and then draw this in red, but I'm doing it backwards now just because I already drew it in red. So this angle right here is the theta we were talking about, and the app just tried to make that prettier and didn't know what I was doing. So there's theta. This little angle in here is d theta. What's going to be our differential area element as seen from above anyways is just going to be this little bit right here. So it's this bit, which looks like a rectangle, but it's sort of not really a rectangle. In fact, the shape is like almost like you cut a piece of pizza and then cut the tip off of it and then cut the crust off of it, and we're just left with this little part. But when you cut the tip off, you did it with a circular arc as opposed to a straight line. Now, the length, as I said, from here to here along this arc is r d theta, where r is the distance from the origin to the front edge, which would be this part right here. So that distance is r d theta. This distance, on the other hand, is just going to be the differential amount dr. So if we pretended this were a rectangle, we could say the area of it is r dr d theta, and that would be exactly right. So that dA that was represented, say, by this area right here, that dA would be r dr d theta. Now, in this case, we actually have it like that as well, except it goes down three-dimensionally like this and appears, in fact, as a three-dimensional object, but that thickness there is just t. You could actually call it DZ if you wanted, and then it would only be infinitesimally tall that way. And then your volume element would be R dr d theta dz. But since the R is what we're integrating, the dz doesn't matter at all because the z, changing it up and down, is all still the same distance away from the origin, which is the rotation axis. So with that in mind, I can now say the formula I is equal to the integral r squared dm. What I'm going to do is say that this little red guy in here is my differential mass element, and that's going to be rho times dv. But my dv is going to be r dr d theta times the thickness t. And I could actually put the t in the front, and that would be fine too, because it is a constant. So let's carry on with this. We're going to say equals the integral of r squared, and then I've got rho, which is a constant, and I have t, which is a constant, and then I have r dr d theta, which means now I'm integrating it twice, once for the dr and once for the d theta. And I'm going to go ahead and pull out the constants in front, and that's going to give me rho times t out in front, and I'm going to say the integral from r equals 0 to big R of r cubed dr, and then the integral d theta from theta equals 0 to 2 pi. Now, I could have put it in some sense like between there, but we generally just shift them to the end and work it this way, as long as we don't have any variables that convolute the dr with the theta. In other words, if we had an r that depended on theta, we'd have to deal with that in a different way. But in this case, it's all easy peasy. What we end up getting is rho, which I already worked out as m over pi r squared t. So that was our rho, and I tried to make it look neater, and it didn't turn out so good. So I'm going to try to make the 2 look better, and then the t. So that's our rho. We also have our t being multiplied by it. Now I have the integral of r cubed is 1/4 r to the fourth. So when I integrate that, it becomes 1/4 r to the fourth minus 1/4 0. So it's 1/4 r to the fourth for that integral. And then the integral of d theta is just going to be 2 pi because we're integrating d theta. That gives us theta. And then we evaluate theta at 2 pi minus theta at 0. So it's 2 pi minus 0, which just gives us 2 pi. So in all of this, we are able to, in fact, cancel out this 2, leaving a 2 down here, cancel out this pi, cancel out this exponent of 4, leaving a 2, but canceling out all of this r squared down there. And of course, we can also cross out the t with the t, and ultimately our result is just or excuse me, it's just 1/2, because the 1/2 is left out in front, m times r squared. So the moment of inertia for a cylinder rotated about its center of mass is 1/2 mr squared, and that time we did it with a double integral. In principle, like I said, you could have done it with a triple integral, uh, and that's not too terribly bad. In fact, let me go ahead and show you just what I would do instead. If I was doing a triple integral, let's write it in black. I would still be equal to the integral of r squared dm. But now what I would do is I would take the integral r squared, and then I'd write the rho, because I got to have the dm, and the dm is r dr d theta dz. So this time the little object that we're doing is a differential mass element, has a little arc right here, and this thickness from here to here is dz. But this part is still r d theta, and this part is still dr. So that's where we get our volume element, which is this part right here. Now I can go ahead and continue by pulling the constants out in front, which in this case the only constant is the rho, which we'll make use of in a little bit. But now I have the integral of r cubed dr, the integral of d theta from theta equals 0 to 2 pi, and this one's from r equals 0 to big R, and then the integral of dz from, let's say, 0 to t. When I complete this integral, plugging in the m over pi r squared t for the rho, the integral of r cubed is 1/4 r to the fourth, so that's going to be r to the fourth over 4, and the integral over theta would be theta. The integral of d theta would be theta, evaluated at 2 pi, and at 0, the 0 gives us 0, and then the integral of dz from z equals 0 to t is just going to be z evaluate t, which is t, and minus z evaluate 0, which is 0. So again, I think you can see that with all the cancellations, this 4 becoming a 2, and this 2 disappearing, this pi disappearing, uh, this r squared canceling out all but the 2 for the exponent there, and this t canceling out this t. So you see again, I get 1/2 m r squared when I do a triple integral as well. So that's it. That's it with the higher math, both in triple and double integrals. Hope that was enlightening, and enjoy it. Bye bye.